Hello, my name is Greg Starr, and I am presenting our work on automated identification of the main ionospheric trough in GPS total electron content images. Our objective is to advance our understanding of the trough by performing a large-scale statistical study using global measurements. To that end, we developed a method to automatically identify the trough at the pixel level in GPS TEC images. Method overview. The input is a TEC image like the one shown on the top left. The dashed line in the images marks the auroral oval as measured by DMSP. The output of the process is a binary image the same size as the input with the positive pixels corresponding to the trough. An example of this is shown on the top right. In the pre-processing step, we convert TEC to log TEC. We then apply a spatial high-pass filter to the image by subtracting a sliding window average. This is shown in the bottom left. The color blue indicates a local plasma depletion, which is a feature of the trough. Next, we optimize a cost function, which models a few key characteristics of the trough in the pre-processed images. An example of the output is shown in plot C. The color red indicates high trough score values. The trough score vector is thresholded. Then we remove positive labels from pixels within the auroral oval and positive regions which don't meet a perimeter or area criteria. The trough image model is designed to capture the relationship between the pre-processed image vector and the trough score vector. Examples of these vectors are shown at the bottom right. There are three aspects of the trough that are captured by the model. 1. The trough affects all nearby pixels in the pre-processed image vector. For a pixel to be classified as trough, there should be a negative neighborhood around the corresponding pixel in the pre-processed image vector. 2. The trough should form equatorward of the auroral oval. The model should generally not assign a high score to pixels that are far from the auroral boundary. 3. The trough should form cohesive regions rather than being scattered across the image. These three characteristics of the trough are modeled by the three terms of the objective function. To validate our method, we compared it to the method described in A2020, which identifies troughs in electron density measurements from the swarm satellite constellation. Treating the swarm troughs as ground truth, we extracted the trough labels from our method along the satellite orbits and checked their agreement. The diagram in the middle illustrates the comparison. The blue pixels mark the trough from our method. The red lines show the troughs identified in the swarm data, and the black dashed lines show the swarm satellite orbits. The table on the left presents the results of the comparison. The methods agree on trough presence around 80% of the time, and there is not a significant poleward or equatorward bias in our measurements of the trough wall latitudes. At magnetic longitudes between 130 and 260, the TEC data becomes quite sparse, and so we don't expect our trough labels to be as accurate. On this page, we reproduce one of the figures from A2020, showing the trough occurrence rate in latitude, local time bins during different seasons. Because our dataset consists of global measurements, these statistics can have a greater level of detail. The general patterns of the two figures agree very well. However, the occurrence rates in the top figure are lower due to different threshold choices. These figures show that the trough occurs primarily at night and more often post-midnight than pre-midnight. Additionally, during the winter, the sunset terminator is pushed back towards noon, which allows the trough to form farther from midnight. On this slide, we show how the trough's latitude varies with Kp. These figures demonstrate a well-known effect where the auroral oval and ionosphere convection pattern expands with higher Kp. This causes the trough to form at lower latitudes. The top figures show the midnight sector, and the bottom figures show the dusk sector. On this slide, we show that the trough's local time appears to also have a dependence on Kp. The right panel of the left figure shows the trough's occurrence rate in local time Kp bins. At low Kp, the trough occurs mostly post-midnight. This can also be seen in the top left panel of the right figure. As Kp increases, the distribution of the trough shifts towards the pre-midnight sector. We believe that this could be explained by an increased number of troughs caused by subauroral polarization streams, but further investigation is required to clarify this relationship. In this work, we developed a new method for automatically identifying the main ionospheric trough in GPS total electron content images. We validated the method against a previously published trough identification algorithm and presented some applications of our labeled dataset. Thanks for watching.